Jai Hind everyone. Today I am going to discuss about the time response specification of the second order control system. So you can see this graph. This graph is representing the time response, transient response specification and the steady state specification of the second order control system. Here the specifications, the time TD is the delay time, TR is the rise time, TP is the peak time, right, and TS represents the settling time, and this MP is representing here the maximum peak overshoot. So the time response of second order system exhibits damped oscillation during its transient response, right? This is showing in this figure. Now I'll discuss all these specifications one by one. I'll discuss all these specifications one by one with their expressions and the derivations. Now let's start with the delay time. Delay time is the time required by the response to reach the about 50% of the required by the input to reach about 50% of the output, right? Now rise time is the time needed for the response to reach either 0 to 100%. Okay, for TR, it is either 0 to 100% of the output or 10 to 90% of the output, right? So this 0 to 100% is generally for the underdamped case, right? And this 10 to 9% basis will be for overdamped case. So we'll go for here for this underdamped case, right? So peak time is the time required to reach the peak value of the output. This can be represented here as this value, this peak. Here we can write it as CT max. Okay, and this maximum peak overshoot can be defined as the maximum positive deviation of the output from its desired value, and the time at which this maximum positive deviation is achieved is called as the peak time, right? So let's start with the rise time, that is TR. So rise time can be defined as the time required to reach 0 to 100% for underdamped case of the output, right, at the very first instant. So we can derive the expression for rise time from the expression of time response of the second order control system, which is CT is equals to 1 minus e raised to the power minus pi zeta, sorry, 1 minus e raised to the power zeta omega n t upon under root 1 minus zeta square up into sine omega n under root 1 minus zeta square into t plus phi, right, where phi is tan inverse under root 1 minus zeta square upon zeta. Now TR, for TR, right, it is obtained at the very first instant when the output reaches about 100%. That means CT will be 1, then T will be TR, right? Put this value in the above equation. We will get 1 is equals to 1 minus e raised to the power minus zeta omega n TR upon under root 1 minus zeta square into sine omega n 1 minus zeta square into TR plus phi, right? So 1 can be cancelled out from here, and this can be written as e raised to the power minus zeta omega n TR upon 1 minus zeta square into sine omega n under root 1 minus zeta square into TR plus phi is equals to 0, right? Since this particular term is finite, so we can write this equation as only sine omega n under root 1 minus zeta square into TR plus phi is equals to 0. So we can write it as sine omega n under the root 1 minus zeta square into TR plus phi is equals to 0. And the general solution for this equation will be n pi, right? So this can be written as omega n under root 1 minus zeta square TR plus phi will be equal to n pi, right? And TR is obtained at the very first instant. So here n will be equals to 1, right? So we can get omega n under root 1 minus zeta square into TR plus phi will be equal to pi. Now from this equation, I can find out the value of TR, which will be pi minus phi upon omega n under root 1 minus zeta square, right? Or it can also be written as TR is equals to pi minus phi upon omega d, where this phi is equals to tan inverse under root 1 minus zeta square upon zeta. So this is the expression for the rise time, okay? Now coming for the peak time and the peak overshoot. Peak time TP and peak overshoot, that is MP, right? As I have told you, MP can be defined as the maximum positive deviation of the output with respect to the desired value, right? Since we know that the time response of the second order system exhibits oscillations during its transient part, right? So these oscillations sometimes exceeds the desired value, and at some instances these the output will be lesser than the desired value, right? So the maximum positive deviation can be defined with MP and can be written as CT max minus 1 if the unit step input is applied, right? And in that case CT is 1, so we can write it as CT max minus 1. And in case of percentage MP, we can write it as CT max minus 1 upon 1 into 100, right? So first we'll do the derivation for the peak time, right? So peak time can be calculated by the expression CT, right? And differentiating the CT and equating it to 0. So we have CT is equals to 1 minus e raised to the power minus zeta omega n t upon under root 1 minus zeta square into sine omega n under root 1 minus zeta square plus phi, right? So now differentiating dCt with respect to t, right? We will get this term will become 0, it's a constant. Now differentiating this term by parts, first this, then this, okay? Then it comes out to be e raised to the power minus, let e raised to power minus zeta omega n t as it is, right? And differentiating this sine term. So it will come out to be omega n under root, sorry, here we have t, 1 minus zeta square into cos of omega n under root 1 minus zeta square plus phi. Okay, plus minus of, this is already minus sign we have here, right? So again minus sign for this and minus sign for the formula. Okay, so now keeping this term as it is and differentiating this term, we will get minus zeta omega n upon under root 1 minus zeta square e raised to the power minus zeta omega n t into sine omega n under root 1 minus zeta square into t plus phi. Okay, this will be the another term. Okay, this is for that, na? Okay. Now taking common e raised to power minus zeta omega n t upon under root 1 minus zeta square will be taken as common from this equation. Okay, so we can write dct by dt is equals to, no, okay, we can take common, but first we will equate it to 0. So dct by dt is equals to 0. That means from previous equation, from this equation, we can rewrite it as minus of this term plus this term, right? So this is minus of e raised to the power minus zeta omega n t upon under root 1 minus zeta square into, right, under root into, what is it, omega n, okay, omega n under root 1 minus zeta square into sine, sorry, cos, it's a cos term, cos omega n under root 1 minus zeta square into t plus phi, right, plus e raised to the power minus zeta omega n t upon under root 1 minus zeta square into minus zeta omega n into sine of omega n under root 1 minus zeta square into t plus phi. So it becomes 0. So we can write it as, we can take here common e raised to power minus zeta omega n is equals to e raised to the power minus is equal to 0, right? So we can write e raised to the power minus zeta omega n t upon under root 1 minus zeta square will be taken as common. Okay, what will be left here? Left term is, here we have omega n under root 1 minus zeta square into cosine of omega n under root 1 minus zeta square into t plus phi. Okay, and from here we have plus of, this will be minus sign, okay, here this minus sign, and this will be plus of, this term has taken common, and okay, it will come out to be again a minus sign. Okay, so this will be minus, sorry, so this will be equals to, here we write what we have taken common is e raised to the power this term, so we have right here, we'll write here zeta omega n into sine of omega n under root 1 minus zeta square into t plus phi. Okay, so it all equals to 0, right? Since this term again here is a finite term, okay, so we can equate this term to 0. Okay, so this will be, I think, this must be a positive sign, right? Because minus sign is from here, minus is outside, right? In the previous equation, let me check it out. See, minus sign is already outside, okay? then minus is for sine formula, and minus came from here. So it will become a positive sign. Okay. So plus into minus, again it comes minus. Okay, minus minus plus and then minus. Okay. Then it come as a minus sign. Okay, it will look okay. This term is okay. So we can write here as, we can take this sine term and this is cosine term. Okay. So we can write here, we'll equate these terms, we'll get, we simply get under root 1 minus zeta, sorry. So this will be plus here. Okay. This come as plus here only. Okay. Because we have minus outside and minus minus plus and then again minus. Okay. So it will come out to be under root 1 minus zeta square. Okay. I am writing down the another term. 1 minus zeta square, right? And upon zeta, I'll do it, I'll do this, this equation I write directly. Here I have taken this omega n will be cancelled out while it goes there, and 1 upon this will become under root 1 minus zeta square. This I have taken this zeta as, and this will be, this term will become the sine omega n under root sine upon cos will become 10. Okay, sine upon cos, sine term directly I'll write here 10. Okay, 10 inverse into t plus 5. Okay, and let me write it as 10. Let me write as 10 of this. Okay, now I will put the value of phi, which is 10 inverse under root 1 minus zeta square upon zeta in this equation. Okay, put phi is equals to 10 inverse under root 1 minus zeta square upon zeta in above equation. Okay, so I'll get under root 1 minus zeta square upon zeta is equals to 10 of under root, what is that term? Under root, sorry, this is 10 omega n into under root 1 minus zeta square into t plus 10 inverse of under root 1 minus zeta square upon zeta, right? So the general solution for this equation will be omega n, right, under root 1 minus zeta square into t will be equals to n of pi, and the peak overshoot occurs at where n here is equals to, you know, n is equals to 0, 1, 2, but the peak overshoot occur at the very first instant when n is equals to 1. So we'll put n is equals to 1 here. At n is equals to 2, we'll get the first undershoot. At n is equals to 1, we'll get the first overshoot. So we'll put here n is equals to 1, right? Then that time will be t is equals to Tp, right? So t will be equal to Tp here. So we can directly write it as omega n under root 1 minus zeta square into Tp will be equals to pi, and from here we'll get the value of Tp, which is pi upon omega n under root 1 minus zeta square, or we can write it as Tp is equals to pi upon omega d. Now the value of peak overshoot can be obtained when we put the value of this Tp in the expression of Ct. So let's try to get that. Since we will get the value of Ct max. Okay, so here I'll write, sorry, Ct, here I write Ct, expression for Ct, which is 1 minus e raised to the power minus zeta omega n t upon under root 1 minus zeta square sine of omega n under root 1 minus zeta square into t plus phi. Now here I will put the value of t, which is Tp, okay, and then I'll put the, here I can directly write this t is equals to Tp, okay, as, and I can put now here the value of Tp in this expression, right, and this is the value for the CT max, okay. So I can directly put the value of Tp, which is pi upon omega n under root 1 minus zeta square upon 1 minus zeta square here, and in this also sine omega n under root 1 minus zeta square into, what is the value of Tp? Pi upon omega n under root 1 minus zeta square plus phi, okay. So this gets cancelled here. Similarly, omega n gets cancelled here. So it will live as 1 minus e raised to the power minus pi zeta upon under root 1 minus zeta square upon 1 minus zeta square into sine pi plus phi, okay. So sine pi plus phi can be written as minus sine phi. We can write sine pi plus phi is equal to minus sine phi, okay. And in the expression of phi, where we have taken, if you remember in the previous expression while we are deriving the expression for CT, we have taken sine phi is equals to under root 1 minus zeta square, right. So we can directly put these two value here, and we can directly put the value of this as minus of under root 1 minus zeta square. So I'm directly writing it out like this, minus pi zeta upon under root 1 minus zeta square upon under root 1 minus zeta square into, this is minus sine phi. So minus sign is here, and the value of sine phi is under root 1 minus zeta square, right. So this value get cancelled here, and this minus will goes here, and it becomes 1 plus, this is simply the value for the CT max, na? Okay. So this will become finally, this will become 1 plus e raised to the power minus pi zeta upon under root 1 minus zeta square. Am I right? Yes, this will become this. Now, we have this value as the value of the CT max. Now, MP is defined as CT max minus 1. Am I right? Right? So, we can put the value of CT max here, which is 1 minus e raised to the power minus pi zeta upon under root 1 minus zeta square, okay, and minus 1, right. This is the value, na, which we are getting here. Sorry, this is the value, okay, I'm sorry. This is the value for CT max, na, and minus 1. So, there's something wrong. Oh, it is plus. This is plus. So, this get cancelled out, and we'll get the value of MP is equals to e raised to the power minus pi zeta upon under root 1 minus zeta square, right. And percentage MP now can be written as e raised to the power minus pi zeta upon under root 1 minus zeta square into 100 will be the value for the percentage MP, and this is the value for the MP, right. Now the last specification is the settling time. It is represented by TS, okay. Since we here also we can plot the graph between the MP and zeta here in this expression, we can see here that the plot for MP and zeta, the value will goes down from 100% to 1 when step input is applied, right? So this will be the value, this will be the graph between MP and zeta. Now starting with the settling time, now coming to the settling time, okay? Settling time, as we know that the second order system, the time response of the second order system is presenting the oscillations during its transient part, right? So the time required to settle down the aforesaid oscillations within 2% of the desired band, 2% of the desired value of the output is called as the settling time, with the time constant of 1 by zeta omega n, right? So settling time can be defined as the time required to settle down the oscillations present during the transient part of second order control system, right? To settle down those oscillations with the time constant of 4 times of the time constant, that is 1 by zeta omega n. This is within the 2% of the desired value. And if we take the tolerance band, it is for 2% tolerance band. And if the tolerance band is of 5%, then the value of Ts will be 3 times the time constant. Okay. So in the question it is given to you whether the value, what we have to take in, what we need to take the tolerance band. Okay. It could be at 3 times of time constant, or it could be 4 times of time constant. That's all for today's lecture. Thank you so much. In the next lecture, I will discuss some numerical based on this second order control system, and then I'll discuss some steady state error on this topic. Thank you.